Hey everybody, I wanted to spend a little time talking about the ideal gas law and what goes into the ideal gas law, so let's get started here. What this formula does is it quantifies the relationship between some of the measurable properties of a gas, like pressure and volume and temperature, and even the number of moles. Okay, so, and we use this guy right here. Pivnert is sometimes how we call it, how we say it, but definitely PV equals nRT, where P is pressure, V is volume, N is the number of moles, and T is temperature. And R is a proportionality constant. R is called the universal gas constant, and that's never going to change no matter what. R is always going to be this value here. Now, it was a little hard for me to do this, so let me just tell you that that unit is written as liter atmospheres per mole Kelvin. Okay, and so notice that it has all the units of all the things that we have that we're measuring, and that way when we use 3 of these to find out the fourth, it will cancel out and give us that unit that we're interested in. So, so this is the formula that we deal with. Okay. Now, the ideal gas law can be used to express relationships. Okay, and so some things are directly proportional and some are inversely proportional. So let's look at pressure real quick. If I were to put pressure here, okay, and then temperature on the x-axis here. Okay. Now, when it says directly proportional, what we mean is this, that it has a positive slope, if you're a math person, or that as 1 increases, as pressure goes up, look at what happens to temperature. Temperature goes up as well, provided that we hold the other constants, the other properties constant. So we have to hold N constant and V constant. Okay, and this would be true also if we did this for number of moles. Okay, N is number of moles. We could also draw a line similar to this, provided T and V were held constant. So that is what it means to be directly proportional. It means as 1 increases, so does the other. Okay. Now the other one is inversely proportional. So if we have pressure here, and then we put volume here, what's going to happen is this. Okay, and the idea here is as we increase the volume, notice that increase the pressure, the volume gets smaller. And so that's what it means to be inversely proportional. We can look at the ideal gas equation, or the ideal gas law, or whatever you want to call this thing, Pivnert, and we can look. This equality tells us whether it's going to be directly or inversely proportional. The idea here is if pressure increases, and we are comparing it to volume, in order to keep it equal, we're keeping this side the same, we're not changing it. So if this one gets bigger, this one has to get smaller. Okay, and the opposite is true. If pressure gets smaller, volume has to get bigger. Something that is directly proportional, PV equals nRT, means that, again, this is equal. So if this increases, that means this side of the equation increases. That means this side of the equation has to increase. So if it's temperature there, provided that this holds constant. Okay, or maybe not this, but maybe this. If the temperature is held constant, the only way to increase pressure is by changing the number of moles, by increasing the number of moles. And so the ideal gas equation tells us whether something is directly proportional or inversely proportional to each other based on where it is in the equation. So let's do a sample problem of PV equals nRT. it's important for us to do this sort of thing. Okay, and I'm going to call it my calculator. And here we have nitrogen gas in an airbag. Okay, and this is actually what happens in an airbag. There's a chemical reaction that releases nitrogen gas quickly enough to inflate an airbag before you hit the steering wheel. Okay, so here's how I'm going to want you to solve these problems. Write everything that you're given. Okay, so 65 liters equals volume. Okay, and a pressure of 829, so 829 millimeters of mercury equals pressure, and a temperature of 25 degrees C equals temperature. And then we want the number of moles, so N equals question mark. Now, if you look, by doing this, we have V, P, T, and N. We have all of the values that we need in order to solve a PV equals nRT problem. The only thing is we have to make sure that everything is in, I don't want to say base units because there are 7 base units and these things aren't necessarily base units. What we have to do is make sure they are in the standard units of measure for that property. So the standard unit of measure for volume is liters, so that one's okay. The standard unit for measuring pressure is atmospheres, so we have to do a conversion problem here. So 829 millimeters of mercury, and then we're going to set up an X line. Okay, this allows us to interconvert easily between the two units that we want. We put millimeters of mercury on the bottom, and we want to go to atmosphere, and we would have to look that up. Fortunately, I know it off the top of my head. It's 760 millimeters of mercury is equal to 1 atmosphere, and so now we do the math. Okay, so we do 829 divided by 760, and that equals 1.09 ATM. Great. So now we have that in the appropriate units. And now temperature, what's the appropriate unit for temperature? The appropriate unit for temperature is Kelvin. Okay, and that is a base unit. So we have to make sure that we do this. So in order to do that, we do 25. And in this is one of the very few conversions that we don't use the X line. And so that's 25 degrees Celsius plus 273. That's the conversion factor. That's going to equal 298 Kelvin, and now we have it in the correct temperature. Okay, 25, I'll do it on the calculator just so you can see. 273, that's 298. Okay, so now that we have our standard units here, now we can do PV equals nRT. So we're going to do, I'll do it in black here. So we're going to do PV equals nRT. What's our pressure? 1.09 atmospheres times our volume, 65 liters, equals N, that's what we're solving for. Okay, that's our question mark, times R, 0.0821 liter atmosphere per mole Kelvin. I'm going to move the calculator up here. We don't need to read the problem anymore. Okay. Times 298K. Now, look at what happens. Atmosphere, liter cancel out. Kelvin cancel out. What's the only unit we have left? The only unit we have left here is moles, and that corresponds, because what does N have to be? What has to be the units of N? Moles. So now what we're going to do is we're going to take and divide both sides by 298 and by 0.0821 and by 298. So 0.0821, 298. Those cancel. It gives us N all alone, which is, that's what we want, and now we do the math. So 1.09 times 65. Okay, now here's the thing. A lot of students, they'll go divided by 0.0821 and then times this. If you're times that, you can't do that because orders of operations are going to make that all messy. Okay, so you either do it stepwise or you have to put a parenthesis in here. Okay, and I'll do it parenthesis this time. Okay, times 298. Okay, and so when I get that, I get n. So our final answer is n equals 2.90 moles. And that is how we do ideal gas law problem.